Sí, perfecto.
Buenos días. Welcome everybody to the first series of conferences of the doctorate school of the Autónoma University of Madrid. First of all, I'm going to introduce to the director of the school, Lourdes Ruiz Desviat, who's going to dedicate some few words for you, all the students and professors.
Well, just to introduce myself, because I'm also linked to this role, and welcome you, PhD students and future PhD students. And I hope you enjoy this seminar series. And I know we have a very distinguished speaker to open up these seminars. And just to know that the doctorate school is open for your questions, comments. We are starting a new period with a new theme in the direction, and we want to improve as much as we can all those things that you tell us that we should improve. So please contact us if you have any comments or suggestions for improvements. And that's all. Thank you so much for inviting me to
Thank you so much for coming, Lourdes. Thank you so much. All the students who want or who need a certification for attendance can give the name and email, and we can certify the attendance after the talk. Okay. So first of all, I'm going to introduce Cristina Tan, who is the professor. Professor titular of our department, and she's going to introduce our speaker, Manuel Yáñez.
Thank you, Carlos. I'm going to give a brief introduction, but before I do that, I would like to thank Manuel for accepting the invitation of our department to give a talk. Thank you very much. And obviously all of you for being here. I presume that most of you already know Manuel, but if someone is being in another planet, I'm just gonna give a brief introduction. I'm just gonna give a few hints for you to understand how active and productive has been his career. So he was a national award and a special award for the undergraduate studies and PhD. So everything started at the very top for him. He was a postdoc with someone who is very famous, especially for theoretical scientists, Popper, this guy with the basis. So he was there. He visited several institutions. He's been the deputy head of the European division of computational chemistry. He's the general coordinator, probably one of the founders of the European Master of Theoretical Chemistry and Computational Modeling, that I think that you have heard about. He's given many plenary talks and invited talks in conferences, many. When I say many, it's many. He's a PhD supervisor of 15, 20, I don't know how many PhDs already, because it's probably the information that I got, it was out of date already.
Not so many, yeah, 15 or
15. He's co-author of more than 400 papers. He's a member of the Spanish Royal Societies of Physics and Chemistry, is of the American Chemical Society and the Royal Society of Chemistry, of the Commonwealth, I presume it is, or the England Society. He's been awarded with several awards: research award from the Autónoma University, research award from the in physical chemistry, distinguished career award from the Spanish Royal Society of Chemistry, not too long ago, in 2018, the research award in France in 2003. He's honoris causa of the University of the Basque Country. He's been given the Lifetime Achievement Award last year in 2024 by the European Chemical Society, and he is in possession of the Cross of Civil Order of the Alphonse Vitel. I don't know which one you are the most proud about, but you can tell us. So thank you for your idea. So thank
you very much, Cristina. What matters is what I'm going to say to you today, and if I try to convince you how interesting can be even the small systems. This is a very special year because it's the International Year of Quantum Science, because the Schrödinger equation was published 100 years ago. And today, theoretical chemistry is just a tool present in practically all the labs around the world. because it's able to calculate, when I was starting my postdoc with Popper, calculate a molecule of initial with more than 3 or 4 heavy atoms was a challenge. Okay, calculate the pyridine was just a miracle. And nowadays we are able to calculate macromolecules in the realm of biochemistry, in the realm of chemical materials. We are able to simulate processes that occur in nanopicofemto and attoseconds. We are able to simulate the movements of the electrons within a molecule. At the same time, the different formalities that have been developed mainly in the last part of the 20th century are able to reach accuracies as high as the experimental accuracy. So we are able to calculate chemical processes, the enthalpies of the free energy of chemical processes with an accuracy of 1 kilocalorie per mole or even less. Of course, but these are very expensive calculations, but nowadays, we can do these calculations for systems near 1,000 atoms. That is what I can. But today I'm going to just focus my attention on very small systems. Very small systems that still have quite interesting and unexpected behaviors or peculiarities. And that could be related with questions like this. The correlation between a strong bond and a high stability of a compound is always fulfilled. Apparently, the question is stupid. You will see that it's not so stupid. Another probably a stupid question, when I was a student, if I asked this question to my teacher in organic chemistry, probably I will never get my grade in chemistry, you know. Is it possible to change a base into an acid? If I did this question in 1968, that I was in the middle of my career, my teacher would say, "What are you talking about? An acid and a base are just the opposite of the properties of a chemical system." But it's possible, or it is possible to change an acid into a base. Well, I will try to convince you that electron deficient systems have a very peculiar chemistry because they are electron deficient systems. The calculations I'm going to show you are always done at a quite high level of accuracy. Normally, the structures are obtained using density functional theory, but the final enthalpies are calculated at G4 or couple cluster simple dash parentheses triples with a complete basis set. That means that we have for sure an accuracy of less than 1 kilocalories per mole. But sometimes we need to understand what is going on. When we have these questions I was supposed to you, how is possible that a strong bond cannot lead to a very stable system? And to understand that sometimes you need to decompose your total energy into components, 1 center, 2 center, 3 center, and so on, to have a view of what is going on. At the same time, you need also to decompose the total energy into the nature of the interactions that are responsible for the stability of a given system. Coulomb interactions, van der Waals interactions, or things like that. And finally, we need to see how the bonds are formed. And to that, the best way to do it is just to look at the electron density of your system, and you can use 4 different approaches that are sometimes complementary: the quantum theory of atoms and molecules, the electron organization function, the adaptive natural density partition, but we don't care about the details. So each time I present that to you, I will mention. Well, one of the main characteristics of the systems that are deficient electron deficient, as boron or beryllium, the 3 elements or the alkaline earth elements, is something that was proposed before quantum chemistry was applied. Was Lewis the one that realized that in most of the elements of the first row, the central atom is surrounded by 4 pairs of electrons. In methane, in water, in ammonia, but in the case of boron and beryllium, you have only 3 electrons in the valence shell, only 3. So you have the possibility of having 4 pairs around the boron, but you can only form 3 because you have 3 electrons that can be shared with other elements that are stable. In the case of beryllium, you have only 2. So the image that Lewis tried to send is, okay, when you have a boron compound, the boron atom has a still place to accept a further pair of electrons. And they call them electron deficient systems. That is not the case neither for carbon, nitrogen, oxygen, or fluorine, or other elements of the periodic system. And that is a clear evidence. If you make this simple reaction, 2 colorless gases, in this part is ammonia, and in this other tube is boron trifluoride. You do that, and immediately you see like a white smoke. That is not a smoke, are very tiny white particles. And these white particles are exactly this compound. You have the boron trifluoride is an electron deficient system. And ammonia has a lone pair of electrons that is not used in the formation of the nitrogen hydrogen bonds. So the donation of the lone pair of nitrogen into the empty place in boron forms a very strong, that we call dative bond, because it's the donation of a pair. Quantum chemistry ratifies exactly the idea of Lewis, because when you solve the Schrödinger equation for the atoms of the first period, you observe that you have as solutions the 1s orbital, n equal 1, there is only 1 orbital, but for n equal 2, you have 4 possible orbitals, depending on the angular momentum of the electron. So you have an s orbital and 3 p orbitals. So in boron, when you form boron trifluoride, you have a p orbital that is empty. So in that orbital, the electron pair of ammonia enters and makes a very strong bond. But the peculiarities of the electron deficient systems also affect to the bond, because one of the things that was surprising for all the chemists at the beginning of the 20th century was when they determined the structure of boron dihydride, because they would expect to observe boron H3, but never saw boron H3. They always saw boron 2H6. How is possible that BF3 can combine with BF3? And the solution was, in that case, the solution of quantum mechanics, because quantum mechanics show that in this particular case, the orbitals of the 2 boron atoms combine with the orbital of the hydrogen, forming an orbital that is a 3-center orbital, not a 2-center orbital like in a NH bond, for instance. 3 atoms are involved and only 1 pair of electrons. So this kind of bridge makes this system stable, and this is how the electron distribution is done. So the charges are, the electron density are concentrated here, making this system stable. But the surprises appear immediately. Well, everybody's happy because we understand why the 2H is stable, but when you calculate the fluorine derivative and you calculate this system, what you obtain is that this system is unstable. It's 45 kilojoules per mole above the 2 molecules separated. Why? In the case of boron trifluoride, the timer does not exist. Well, everybody assumed that this is true for years and years, so you could read papers saying, it is well known that boron 2F6 do not exist. But it exists. But what you obtain when you do quite reliable ab initio calculations on the system is this structure. But this structure is a weakly bound timer. When your program make the drawing, put you that there is an interaction here and here. But when you look at the electron density distribution of the system, you realize that these bonds do not exist because that is the structure. So there is an interaction between this fluorine atom and this fluorine atom, but the fluorine atoms are not connected with the boron atoms. It's just pure dispersion. That is a very weak interaction. And actually, you can calculate using these partitions I mentioned to you that the dispersion accounts for more than half of the stabilization energy. But, and what happened with the trimer? Well, the triborane exists. The triborane has been observed. The triborane is very stable, but this guy is not. Again, what you have is this very weakly bound species. When you look at the electron density distribution, you see that in triborane, you have very strong boron-hydrogen bonds. This is the electron density. But when you look at the fluorine derivative, the densities are as high as in the triborane. Why this guy is stable and this guy is not? These bonds are very strong. Why this guy is not stable? Why this guy, where the interactions are very weak, is stable and this is not? Well, the first thing we have to remember is that BH3 or BF3 is a planar structure. sp2 hybridization, and all the atoms are in a plane. But when you form the interaction of this guy with an ammonia molecule, you need to put your electrons in an empty orbital. The empty orbital you have here is a p orbital that is not engaged in the bondings here. So these are the orbitals that form the three boron-hydrogen bonds, and this is empty. So to put electrons there, you have to pay certain amount of energy, because this is a stable orbital, but this is not. So you have to mix this with this, but this is much less stable than that. The mixture has an internal stability, but you have well, so doing this mixture has an energetic cost. You have to change for sp2 to sp3 hybridization, and that costs energy. When you calculate the energy, you see that you have to pay, in the case of BH3, 94 kilojoules per mole. But in the case of the fluorine derivative, you have to pay much more energy, 169. Why? Well, the reason is very simple. Fluorine atom is a very electronegative atom, and therefore the orbitals that form the three BF3 bonds is much lower in energy than that of the hydride. So now the amount of energy you have to pay to combine this with that is large. What happened then? Well, when you make the analysis of interaction energy in terms of the 1 center, 2 center, 3 center terms, well, when you look at this guy, you see that the amount of energy you have to pay to change the hybridization of the three boron atoms is very large. Of course, you are forming strong bonds, so the energy you gain forming these bonds is also quite negative, but not enough to compensate this cost. So this guy has very strong bonds, but not enough to compensate the energetic cost you have to pay to rehybridize the bonds. What happened with the weak compound? Well, in the weak compound, the distortion of the boron fluoride is practically zero because remains planar. The interactions are very weak. So this value, instead of 164, is less than 1 kilojoule. And the interaction that is weak because it's a van der Waals interaction is enough to make the system stable. So you have a guy with very strong bonds that is not stable and another guy with weak bonds that is stable. If you go now to the aluminum derivative instead of boron, the situation is similar, but the interaction, the stabilization is a little bit smaller. But when you go to the trimers, in the case of the aluminum, one thing changes. In the dimer of the aluminum is less stable than the dimer of boron, which is normal because aluminum is much bigger, the bonds are longer. But in the case of the trimer, it's the other way around, because this guy is more stable than that guy in relative terms. And the reason is very simple. Here, your program designs 5 bonds, and here also designs 5 bonds. That's your program that makes the drawing taking into account only distances. But when you look at the electron density, you realize that in this trimer, the boron is only 3 coordinated. It's forming the green spheres, shows you the existence of a chemical bond. Is only forming 3 bonds around, while in the aluminum case is pentacoordinated, and that is why this guy is more stable than the other guy. Well, it is possible to change a conventional base into an acid. Well, the concept of acid and base is very old in the history of humanity. Acidus in Latin means agrio, because at the beginning, the way you distinguish an acid from a base was the sense, the odor, the taste, and all we have before the middle of the 20th century on acids and bases were acids and bases in solution. After 1975, it was possible to measure the acidity and the basicity in the gas phase. What that means? When you are measuring the basicity of ammonia in water, you are not looking at the basicity of NH3, because NH3 has been solving water, has interacted with water, and its properties have changed. If you measure it in the gas phase, you are measuring the basicity of the NH3 molecule, and the result is different. In the gas phase, the strongest base in the amine groups is the 3-methylamine. In solution, is the weakest one. In water, in the liquid phase, water is neither a base nor an acid. But the water molecule is the base. Well, taking that into account, let's go back to the reaction I showed you. Well, if you look at this process, in this molecule, ammonia, you have a hydrogen bonded to a nitrogen. This is more electronegative than the hydrogen, therefore the hydrogen has a positive charge, partial positive charge. But when you go to this compound, part of the electron density of nitrogen has been sent to boron. So the electronegativity of the nitrogen atom has been enhanced because has lost electrons in the donation. So it retires more electrons from the bonds with the hydrogen atoms. Therefore, the charge, the positive charge of the hydrogen atoms in this complex are larger than in the isolated bond. So one should expect ammonia to be a stronger acid if it is combined with BH3 or BF3. This assumption was ratified experimentally in Madrid and was using phosphine borates. Phosphines are bases like amines, phosphorus instead of hydrogen, of nitrogen. And when you measure the acidity of the phosphines, it's very, very, very small because they are bases. But if you form the phosphine borates, compounds like this, but with the phosphorus here, the acidity increases between 80 and 110 kilojoules per mole. This is a huge amount of energy. And to give you an idea how huge it is that in terms of the equilibrium constant of the reaction, the increase is the 18 orders of magnitude. So the acidity increases 100 million times with respect to the isolated bond. So ammonia, that is a base, can be a strong acid. Well, if you go now to the alkaline earth derivatives, the situation is the same. It's the same, and you see here you make the reaction of NH3 with BH2, you form that. This is the negative bond, you get this energy. But what is also obvious is that if you deprotonate your base, when you form this atom, the interaction is much, much stronger. Because in this case, you have a lone pair that is donated to the beryllium. But in this case, the system that is donated to the lone pair is an anion, has lost the proton. So it's a much better electron donor. And therefore, the bond is much stronger here than here. And as a consequence, the acidity, the smallest is number, the largest is the acidity, increases dramatically. Increases 200 kilojoules per mole. In terms of the equilibrium constant, 22 orders of magnitude. So you have an ammonia molecule that is more acidic than phosphoric acid. But this is not new with respect to the first thing. What happens if you look at the dimer instead of the monomer? What happens if your molecule interacts instead of BH2 with B2H4? If you look at the molecular electrostatic potential that gives you how is the electrons distributed there, this black belt that is here corresponds to pi holes, to regions where the electron density is very, very small, where the electrons used to arrive. But in the dimer, you lost this symmetry because this is linear. You observe just the two holes over the boron atoms. And the value, the depth of the hole is much larger. So the dimer should be a better Lewis acid. And indeed, what you see is that the interaction energy, that is with respect to the monomer, increases, but increases more for the deprotonated species. So, when you have the neutral interact with this guy, and the interaction is 29.3 kilojoules per mole larger than the interaction with this one. But if what interacts with that is not NH3, but the anion NH2 minus, the interaction increases 100 kilojoules per mole. Why? And again, the quantum chemistry has the answer. This is the atom of the neutral system, But as soon as you remove the proton here, you have a second lone pair free. And the second lone pair interacts with the other beryllium atom, and instead of having one, you have two bonds, and therefore, going from the monomer to the dimer, you have a further increase of the acidity. So ammonia interacts with the monomer and is more stronger than phosphoric acid, but interacts with the dimer and is as strong as sulfuric acid. If you go to the trimers, the situation is the same. I'm going to skip this because it's more. What about the basicity? Well, if you have this complex ammonia BH2, I have two possibilities. How to protonate that? You can protonate the base. That should be the thing any chemist would expect. You protonate the base. Or you protonate the acid. For my teachers, that would be stupid. Well, the first thing you observe is when you protonate the base, this is instead of ammonia now is NH4 plus, the ammonium ion, you observe that the hydrogen bond is formed between this cation and this neutron. This hydrogen is very positive charged, and this hydrogen is negatively charged because it's bonded to a metal, to beryllium. When you protonate in the beryllium, actually what you observe is that actually you are protonating one of the hydride bond to the beryllium in such a way that your complex is this interacting with a hydrogen molecule. In chemistry, we call that a hydride abstraction reaction. You put a cation, that removes it. Well, the surprise is that this process is more favorable than that process. It's better to protonate the acid than to protonate the base within the complex. And to understand that, this is a thermodynamic cycles that give you all the key factors. Okay, in the first process, sorry, in the second process, in the hydride, the thing you have to do, that is your starting point, okay? And you are going to reach this one. That is the reactive, you protonate it and you get here, okay? But instead of doing that, I can do that making calculations. You know? The first thing I need to do is to have an H minus. To extract an H minus from here requires a huge amount of energy because I am breaking a very strong bond. But once I form H minus, when I protonate that, what I form is H2 molecule for the interaction of hydrogen ion and a proton. And that is a very exothermic reaction. So I reach this point when I have, this is the guy that lost the anion, the H minus is a cation interacting with the H2. Now the interaction of this guy with this guy is very weak. It's just dispersion and polarization, and you get that. Now let's protonate the base. Again, this is the starting point, and this is the end. In this case, I'm protonating here, and I reach this complex. So here, the first thing I need to do is just to detach NH3. That is also endothermic. Now I have to protonate NH3. That is very exothermic because NH3 is a good base, and I get here. And now I have this weak interaction and well, but this value is larger than that value. So this process in which I am protonated the beryllium part of the complex is more exothermic than this one because this term is so exothermic that compensates that the other terms are more endothermic. So when you see using increments in the basicity, and just to give you some values, no? With the dimers, you have, for instance, in the case of magnesium, acidities that are larger than the perchloric acid. But, this is just to mention that we explore exactly the same problem using the borane instead of the dimer of beryllium, but nobody first studied the possibility of studying the basicity of the borane. The borane, this structure I showed you at the beginning, but it's clear that when you make the interaction, for instance, between ammonia and BH3, you are changing the electron distribution of BH3, and BH3 goes from planar to pyramidal because of these changes. But it's obvious that the NH3 also changed its electron distribution significantly. How this affects the basicity of the system? In other words, can be beryllium or boron bonded to a nitrogen base, a base? When I talk with my colleagues of the idea of studying this, they told me an electron deficient system, by definition, works to accept electrons, not to accept protons. But can accept protons and very efficiently. To make that study, we decided to use the borane, that is another form of the dimer of boron, with 4 hydrogens instead of 6. And the reason was because we saw that this compound, the borane, interacting with nitrogen bases, increased the acidity of the nitrogen bases up to 50 or 58 orders of magnitude. So when B2H4 interacts with ammonia, pyridines, or other nitrogen bases, these bases are significantly more acidic than perchloric acid. That is the strongest acid known, that is an oxygen acid. But what about the basicity? This guy was studied many years ago. Actually, was Curtis and Popper in 1989 that found, in opposition to what was believed by everybody, that this structure in which you have 2 hydrogen making a bridge between the 2 boron atoms was the most stable structures of this compound. Up to 1989, everybody was studying exclusively these 2 symmetric forms as the possible form of B2H4. But this one is more stable. Our calculations at the couple cluster simple double stirred CDS shows that is indeed the case. And the peculiarity of this guy is when you look at the orbitals of this compound, you see, you made your calculation, and here you see the 3 center 2 electron orbitals responsible of the 2 bridges, and here in blue, another orbital that is between boron and boron. It's like a double bond, boron-boron. But this double bond is a little bit peculiar, because when you look at the electron density, you observe that here there is a maximum in the electron density instead of a minimum as in a normal chemical one. The maximums are over the nuclei. The maximum of density is there because the attraction of the nuclei is maximum over the nuclei. And here the maximum is in the middle of the bond. It's what called non-nuclear attraction center. So this bond has a peculiarity that is also observed when you make the ELF. This is the distribution of the paired electrons calculated. The green one, these are of the boron hydrogen bonds, and the green ones normally are used to describe lone pairs. But this is it's not a lone pair because it's an orbital between boron and boron. But the density is concentrated in the middle of the bond as if it was a lone pair. And the electrostatic potential is very, very attractive in that. Not surprisingly, when you protonate this guy, you obtain this symmetric structure that is B2H5. But when you associate this compound with a base, the important thing is that the new complex this is the complex with ammonia, it still has this feature. This orbital remains there. Now there is not a non-nuclear attractor, but as you see, here is again this kind of lone pair. The density is exactly the same as the one we have in the B2H4 isolated, but there is a difference, that the volume of the area is much smaller. So this lone pair is much a lone pair. And accordingly, the electrostatic potential is more negative. If you increase the basicity and you use instead of ammonia guanidine, the effect is even stronger. You see, this is still smaller than that, and this potential is more negative. When you calculate the all possible protonations, these are all the possibilities. So you can protonate here, you can protonate here, protonate here, you can protonate on the ammonia, or you can protonate on the boron. And when you protonate on the boron, you obtain the most stable one, and the difference is larger than 100 kilojoules per mole. What are the proton affinities? When you look at the proton affinities, this is the proton affinity of B2H4 isolated. This is a stable compound that has been measured experimentally, and the value, calculated value, agrees with the experimental one in 0.2 kilojoules per mole. But you put ammonia, and you have an increase with imine, with HCN, but with pyridine, we saw a basicity above 1,000 kilojoules per mole. And 1,000 kilojoules per mole is like a magic number. The people that measure basicities, all the bases that have a proton affinity above 1,000 are considered super bases. So, we say, B2H4 is a super base. And then we thought, okay, what happens if we introduce bases that are stronger bases that within the complex? So you put one in, and the basicity is 1,043. But 1,043 is the other magic number, because the strongest base characterized up to now is this compound. It's a nitrogen with a naphthalene ring, in which the proton is combined directly with the two lone pairs of the ammonia. But this base has a proton affinity of 1,028. And we are talking about of 1,043. And if you use, instead of guanidine, 1,2,5-trimethylene 1,062. So I have an electrodeficient system that is 1,000 times stronger as a base as the proton sponge. This molecule is called proton sponge because when you tap the proton, well, this electrodeficient system is a better proton sponge than the proton sponge. The same happened when you look at the derivatives of the B2H4. I'm going to pass this very, very quickly. You see, you have proton affinities of 1,128 kilojoules per mole. In this case, because when you protonate this guy, you release a lot of the strain on this system, but I'm not going to enter in this. I want just to finish showing you something that has been done as a consequence of all this analysis. One of the critical problems we are facing now is the warming of our planet, even though there are very important conditions that certain issues. Science, is very young. So one of the possible solutions is to absorb CO2 from the atmosphere. But there is a problem with that. It's like producing hydrogen, you know? Of course, we can produce hydrogen. The only problem is that hydrogen can produce either from water, or from ammonia, or from methane. So methane, don't touch it. But to break an oxygen-hydrogen bond or a nitrogen-hydrogen bond requires a huge amount of energy. And therefore, to produce hydrogen is possible from water and ammonia. Of course, it's possible, but it's at present too expensive. The other thing is to reduce the amount of CO2 we have in the atmosphere. But CO2 has another problem. It's a very unreactive system. Carbon is oxidized at the maximum CO2. So CO2 is almost an inert gas. It's very difficult to react CO2 with anything. But my colleagues from the National Research Council, Ivonne Alcorta, Alguero, and others, said, okay, why we try to think in materials like this one? This is graphene, it's a shell of graphene. And now let's dot this graphene with, for instance, boron and phosphorus. You realize this is an electron diffusion system. This is an electron-rich system. Okay? What happens if I make in the interaction between this molecule with CO2? Well, the first important thing is that CO2 interacts with both atoms because the carbon atom interacts with phosphorus and the oxygen atom interacts with boron. The oxygen atom of CO2 is an electron-rich system, so donates the charge to the boron atom that is electron deficient. The carbon atom of CO2 is an electron deficient system because it's attached to two very electronegative atoms and retires charge from the phosphorus that is a base, a rich system. The most important interesting result is that if you put two molecules or three molecules, because you have enough centers, there is a kind of cooperativity, because as soon as your system is donating and withdrawing charge, the second one, these properties are increased with respect to the first one, and the third one respect to the second. And therefore, the energies increase significantly, and therefore, it could be possible to retract CO2 from the atmosphere using this kind of mechanisms. And so, just to finish, it is very important to distinguish in chemistry between what we call specific properties of the molecules and the properties of the molecules they show when they are in solution, the intrinsic properties. So water is intrinsically a base. In solution is neutral. Ammonia is intrinsically a base. In solution is a stronger base than the 3-methylamine, and should, because 3-methylamine intrinsically is a stronger base. The reverse is also true. When you do simulations using quantum chemistry, and you try to explain or to compare your results with experiments, if the experiments have not been done strictly in the gas phase and at a low pressure, gas phase means that you are going to interact directly with the molecule. But at the same time, that molecule is not going to interact easily with other molecules. So it's not enough to have it in the gas phase, but at low pressure. Your comparison can be completely wrong. Because you are looking at the properties of an isolated system that in the experiment is not isolated, that is interacting with the environment. Well, there are factors that you cannot never forget. Rehybridization. It's terrible to open a journal and to read the paper where the author said, and this guy that was planar demineralized because of the steric hindrance. Steric hindrance. If it was planar, there are no steric hindrance at all. It demineralized not because there is no room for the other system. Demineralized because its electron density distribution has dramatically changed because of the interaction. Or we cannot forget dispersion. You know, I gave a lecture in the Royal Academy of Sciences saying the enormous importance of weak in chemistry, because most of the most important properties of the molecules are related with weak interactions. Water is liquid because of a weak interaction. The ice is less dense than water liquid because of a weak interaction. The ADN can replicate because of a weak interaction. You know, if you forget the weak interactions, perhaps you are forgetting the most important component in the system you are looking at. In the case of the dimers of BF3, there are many papers saying simply these dimers do not exist. Do not exist because you never try to include weak interactions that can make them be stable. And okay, you can change a base into an acid and an acid into a base. You can make many interesting things, many things that are still to be analyzed. In the archive at present, there are classified 237 millions of molecules. You know, our planet is a singularity because those molecules do not exist before the Homo sapiens. 237 millions. You know how many could be possible? Okay? Above 10 to the 60. So there is a lot of work to be done. And just to finish, I have to thank everybody that collaborated with me, in particular my students of Master of Doctorate. I start with Leticia, that is now full professor at the University of Vienna after more than a decade. That started with me the study of dissociative protonation processes, or Marcelo Hurtado, that was engaged in this first paper that proved that phosphine boranes were more acidic than phosphoric acid. The person with whom I must share my whole professional and personal life, and then in the recent papers I showed to you, published in the last 3 years, Montero, that is now got a position in the National Research Council, Professor Alcorta and Professor Elguero, that are professors in the Institute of Medical Chemistry in the National Research Council, but they do theoretical calculations and analyze many of the systems. And thank you, all of you, for being here today.
Thank you, Manuel. Very nice talk. It would have been a very nice talk for analysis last year. Anyway, previous years for the master studies that we do analyze the talks. It would have been a very nice one. Proper chemist, actually. So it's open for discussion. So questions?
You can ask questions.
I have one question related to water, because you have said that water is neutral, liquid water, I guess.
Yeah.
With temperature, for example. But I have read that the Robert Taft reported the acidity and acidity scale, and according to Robert Taft, water is acidic and not basic.
Well, let's say.
Can you get more information on that? Because
But it is true that, as I said, for instance, NH3. Experimentally, one can measure the proton affinity of NH3. Okay? But you can also measure experimentally the proton acidity of NH3. That means you can put in your mass spectrometer NH3 and protons to form NH4 plus, but you can, in the same and with the same experimental setup, to put systems that detach a proton from ammonia. So ammonia has a proton affinity and has an acidity, has a basicity and has an acidity. So ammonia is a stronger, quite a strong base, and is a very weak acid. Water is a weaker base than ammonia, but a stronger acid than ammonia. How can you say that the acidity is greater than the basicity? Escapes me, because the scales are completely different. What I mean is, when you protonate ammonia, you put a proton that attached to the lone pair, and the reaction is exothermic in 860 moles, kilojoules per mole. When you detach a proton, you have to break an NH bond. And that process is very, very endothermic. It's of the order of 1,600 kilojoules per mole. That is twice the so from that I could not say that is more acidic than basic. Only if you compare it with other systems. I can say that is more acidic than ammonia, but more. It is a stronger acid than a stronger base.
it was reported long ago. I don't know, because you have been working with Robert Taft long ago, that the acidity of water is 0.
Well,
liquid water, not gas.
That's right. But that's well. When the measurements in the gas phase were appearing in the literature, that was a surprise. It was a surprise that water behaves like a base in the gas phase, isolated. It's protons in a very exothermic process. But water, liquid water, is neither basic nor acidic. So when I try to explain that to my students, I say, okay, what is water liquid? Which is the ensemble of water molecules. Right. So if my water molecule is a base, why the ensemble is not a base? For me, so there is only one possibility, that this water molecule is a base, but two water molecules are not identical. Let me put it another way. Okay, this is my water molecule, isn't it? Liquid water, thousands and millions of trillions the water molecules. But in that reasoning, we are forgetting something important. This water molecule, when they are at different distance, are identical. When you approach them, they are not. Because in the dimer, one of the water molecules donate the proton to one of the lone pairs of the other water molecule. And therefore, this water molecule is different from the second water molecule. Because this water molecule has an OH bond longer than the isolated water molecule. And the other water molecule now is a better proton donor because it's receiving another one from the other water. So in that process, you are changing the basicity of this water molecule and the acidity of this water molecule. That is the reason why the ice is less dense than the liquid. Because when you form the trimer is not one water molecule, another water molecule, another water molecule. They are not linear. They form a triangle. And they form a triangle because the first water molecule is a better base. So the first water molecule finds an oxygen that wants a proton, no? So donate that. But it themselves has an oxygen that sees another water molecule that is better donating the proton. So at the end you have a triangle in which you have this water molecule as a acceptor and donor. This water molecule behaves as acceptor and donor. And this water molecule behaves as acceptor and donor. So the three hydrogen bonds you are forming are stronger, the three of them is stronger than the one you have in a gas. What happened? That the volume you occupy with three water molecules is much larger, that's 3 times the volume of one water molecule, much larger. Therefore, when the water molecules start connecting each other because they are cooler and cooler and cooler, they form a structure that has a volume much larger than the water, that is ice. That is not only less dense than liquid water, but while liquid water is colorless, ice is white. And that depends also on the formation of these agglomerates. So this kind of cooperativity is very common in chemistry and explains many different phenomena, but as simple as that. So in this process, if you start doing the game, you are seeing that as soon as you put water molecules to interact with water molecules, their initial basicities and acidities are converging to the time that at the end all of them behave with an equal strength as proton donor and proton acceptors, corresponding to our idea and evidence that water molecule is the neutrality absent. Thank you so much.
Yes, a question, I think. And I encourage you to ask something. For this molecule that you talk like the proton sponge, because one of the things that you have actually seen in obviously in the gas phase, everything is different and is pretty much dependent on the fact that
on the values having the gas phase.
Yeah.
Okay. So when I say that this molecule has this proton affinity, that's his measure. That's in experimental value. Okay.
This is experimental value in gas phase, and what it will be this value in liquid phase then? Well, liquid, no. Because that would be more dramatic than in a small.
It's still a very strong base, okay?
Okay.
But when you go to the gas phase, to the solution, there is a huge attenuation of the property. Because this guy is now, when it is protonated, has a proton that is bound between the two nitrogens, okay? This proton is like a tennis, so the proton that is there. But as soon as you put this in water, this proton is now filling the interaction with water, and the oxygen of water is taken. So this is completely distorted. The stability of the system in the gas phase decreases when you go to solution, and therefore the Heinz basicity you see in the gas phase is much smaller in solution. And many of these processes disappear in solution.
Yeah, because in that case, because of all these analyses that you've done about the density, obviously in the small molecules, it's a little bit more restricted because it's small, but in these that is super big, it would be more dramatic than in a small molecule. So the change between the gas phase and the liquid phase, it would be quite bigger, I presume, in this molecule. Is this what you see?
Yes, because when you have a small molecules, the secondary interactions with the solvent are much smaller than in this guy, because this guy has all these rings, has two methyl groups here. Now you have a proton there, so all those groups are interacting with the solvent, and therefore they are changing the electron density distribution, not dramatically different from the gas phase, but significantly different from the gas phase. And therefore, when you solvate the methyl groups, for instance, their ability to donate charge to the nitrogen also decreases. Yeah, because you have the methyl groups have no much charge, carbon is not very electronegative, but now the hydrogen atoms attached to the methyl group are surrounded by water molecules. So these hydrogens are changing their electron density distribution. Therefore, they are changing the electron density distribution of the carbon that is bound to the nitrogen. So you are changing the whole system. You are many changes are very significant in a single point, but actually they are practically affecting the whole system.
And obviously, it's not what you have been studying, but have you checked different results with different methods? Do you see many differences when you study this sort of thing with it?
Sure. When you go, for instance, from beryllium to magnesium, but it's normal that beryllium is a metal, but magnesium is more metal than beryllium. And therefore that this difference are reflected clearly in the electron density distribution. Okay, when you look at lithium, you can understand why lithium is a metal, no? Because in principle there are no so large changes. You start with hydrogen, 1 electron, helium, 2 electrons, and lithium, and it's a metal. Well, it's a metal because when you solve the equation, you have the third electron, because of the exclusion principle, cannot be seated in the 1s orbital, is seated in the 2s orbital, but the 2s orbital is in the stratosphere, right? It's down there. So the electron that is there is not looking a nuclei with 3 protons. It's looking a nuclei with 1 proton and something. So it's very, very much less attached than the ones, so behave like a metal. Then there are other things that depend on other characteristics. For instance, one of the big successes of quantum chemistry was the periodic table as we know it, when solving the Schrödinger equation for hydrogen molecule explained clearly why 2 hydrogens form H2 and why 2 helium atoms never form a helium molecule. Okay? If you go to the periodic table and you go to Mercury, Mercury is like a helium huge because it has 2 electrons in the CS orbit. With that, you would expect Mercury to be like a rare gas. But you cannot forget that has 90 or 90 electrons. So the inner shells, the electrons are experiencing a Coulomb field huge. They are moving at the speed around 1/10 of the speed of light. So your model, if ignore these features, ignore relativistic effects, gives you a wrong description of your system. But if you include them, then your model is telling you, indeed, this is like a helium, with 2 electrons in the s orbital that doesn't want to connect and to make mercury molecules. It's a liquid, of course, because the mass is huge compared with the helium. And that is a liquid that is not wet, because The mercury atoms doesn't want to interact with themselves or with any other else. So they are completely different from water as a liquid. If you go with the same analysis, you arrive to gold. Okay, gold, nobody cares about gold. Gold is very stable. It's known more than 6,000 years ago. That gold is very stable. Gold does not react with anything. But gold is the element before mercury in the periodic table. That means has one electron in the SO. So if quantum chemistry is coherent, one hydrogen atom and another hydrogen atom form a hydrogen molecule. One gold atom and another gold atom should form a gold molecule. Yes, it forms a gold molecule. And that has been proved 3 years ago by Torbrink in Sweden. But the important conclusion was not that. Was when you look at the gold molecule, 2 atoms of molecule, and you look at their properties, their electron density distribution, and you compare it with chlorine molecule, your calculations tell you that gold molecule is much more reactive than Cl2 one. And it is. Because if you now calculate the trimer, the tetramer, the pentamer, and you form cluster up to 100 atoms, those clusters have an electron density distribution that makes them extremely reactive. And now, since then, gold is used as a catalyst, for instance, very specific for green chemistry, because they do not distort dramatically the reactants when they interact in the catalytic process. That was there from nobody thought, well, do the gold molecules exist? They exist. And they have been detected in the gas phase. That's it.
Questions? Extra questions?
Well, I just want to have more insights in that concept of non-nuclear interaction. I think it's from Kutane, no?
No nuclear attractors.
Yes. Okay, I don't fully understand because I know that in Kutane you have the property of the cost condition near to the nuclei. So from where comes that?
What I told you is that it's not into the faculty. Okay, when you look at the electron density distribution in a hydrogen molecule, you have a proton here and another proton there. Okay, and now you have 2 electrons. And when you look at the electron density distribution, you see something like that. There is a peak here and another peak here, and here there is a saddle point in the middle of the bond that we call bond critical bonds. Okay, that's the normal thing in a chemical bond. This and some others are an exception that has something to do with a theory that I do not dominate at all. This is the catastrophe theory. And you realize that because you can simulate what happened with electron density distribution. That has been done by another guy that is very, very, very expert in this particular field. It's Ángel Martín Pendas, that is professor at the University of Oviedo. And now, if you look at the electron density distribution of the atoms, and you realize that when the bond has not been formed yet because they are quite far away, the overlap between this state and the overlap between this state gives you an intermediate maximum. There is no nuclei there. That is what we call non-nuclear atom. There is and that is because it's like some metastable situation in which you are concentrated the density in the middle. That disappears as soon as you change the distance. And actually, when you put an ammonia molecule, this non-nuclear attractor point disappears. But in the isolated molecule, it exists. But a proof that it exists is that when you put a proton, when you protonate the system experimentally, the proton locates exactly in the middle of the middle bond. So the proton see this maximum in this, but this is a very special situation.
So you were talking about the CO2 absorption, right? CO2 absorption. So there you are doping the material with the boron and phosphorus, right? And I'm just curious, like how feasible is the doping?
Right, that is a very good question. That is one of the advantages of doing theoretical chemistry. Yeah, because theoretical chemistry allows you to explore things that are possible or things that are not possible. I'm sure that this is possible. I don't know if it is easy, if it is cheap or not. And that I cannot answer that. But I said it's an advantage because, when you explore things from the theoretical point of view, and then you try to convince experimentalists to look at the result you have found. For instance, the case of phosphine boranes that I told you, the enhanced acidity, the calculations were before the experiment. But I remember a talk by Pekka Pico and Esther in relativistic quantum chemistry that tried to convince a colleague that a phenomenon related with the relativistic effects to make the spectroscopic exploration, and he saw in a congress, the picture of the lab active. And the picture of the lab was that the lab was totally destroyed, the spectroscope, everything, because the system was metastable and exploded during the experiment. So for the theoreticals, it doesn't matter if it is explosive, it doesn't matter if it is toxic, it doesn't matter if it smells bad or not. It doesn't
blackout.
So, but that allows you to explore ways that are very difficult to explore from the experimental viewpoint. Nowadays, one of the most probably large applications of quantum chemistry and computational chemistry is just the simulation of phenomena to guide future experiments. For instance, one of our doctors works in a Belgian company that is producing drugs and cosmetics and things like that. Can you imagine the cost in time and money of exploring the synthesis of some possible agent without knowing if at the end it's going to have the properties you expect? So nobody do that. What happened? They have a group and say, okay, let's look at it. If you put this subsequence in this guy and you include it in that, what properties they have? It is very reactive. It is acid, and then you can then say, okay, now I have selected 3 or 4 candidates and can work on that without any problem and obtain good results. That's it. And the other way around is also true. One of the problems with experimental chemistry, in particular when you are looking to intrinsic properties, is that you can measure nowadays the thermodynamic quantities with high accuracy. So you work with people that work in mass spectrometry, and they are interested in seeing, for instance, how mercury interacts with the amino acids, for instance. Because mercury is very toxic and nobody knows what it is. And then they put amino acids in the apparatus, they put the interaction with mercury, they know what they put, and they know what they saw at the end. They have no idea what happened in the middle. Why the mercury apparently attached to this one, and how I saw the loss of N2, or the answer, only one. Let's explore the possible mechanism of the possible chemical reactions, doing quantum chemical calculations, trying to explain why when you put this and this, put yourself this and this, and you know yourself this and that and that. I am selling washing machines.
Well, if there's no more questions, let's thank Manuel again.